semantics for weak memory.
Okay. Good. Okay. Right. Hello, and thank you all for coming. This is joint work with Victor Vafiadis, both of us at the MPI-SWS Institute in Germany. And as the title suggests, this is about persistent memory. So let's start with a brief history recap. In the beginning, life was simple. We had sequential programs, and PL researchers were happy. Then at some point, we decided that's way too simple for us, so we moved on to concurrency. And with that came the idealized setup of sequential concurrency, sequential consistency, otherwise known as interleaving concurrency. Then at some point in future, we decided even that's too simple for us, and we opened this whole can of worms called weak memory concurrency. And it got really hairy, and this is why we have this whole session today. But as if that wasn't enough, we decided to go one step further and combine persistent memory with weak memory concurrency. And this is when we decided we're going to write an OOPSLA paper about it. So what is persistent memory? So traditionally, you have your programs. They interact with memory. They read and write from memory. So if initially all locations are set to 0, if x is 0, if I run this program and assign 1 to x, afterwards I will have x is equal to 1. And as many of you know, the memory is volatile in a sense that if there are any power failures or crashes, all my work will be lost. So if I restart the program, I will see x equals 0, the initial value. On the other hand, with persistent memory, the situation is different. Things are persistent. The hint is in the name. So if there is a power failure, so long as there is an appropriate recovery mechanism, it's possible for me to recover some of the work I did prior to the crash. So after the recovery, it's possible for me to observe that I had done this work to make x 1. Now, some of you may be wondering, it's either persistent or it isn't. So why is it still possible for me to see 0 after recovery? And the answer is that in many of the persistency models out there, the execution of a program is separated from the act of persisting into memory, which means that when a program executes a write instruction like that, it doesn't wait for it to be persistent to memory. It goes ahead, and this write is instead added to some persistence buffer that will eventually be committed to main memory. So a very simple sequential hardware layout would look like something like this. So traditionally, I have my CPU interacting with the volatile memory. If I write to memory. If I read from memory. And if there is a crash, I lose everything. Whereas in this class of persistent memory, you additionally have this persistence buffer sitting in between. So if I write, I will write to the persistent buffer. And if I read, I first check the persistence buffer to see if there are any pending writes to be committed. And if not, I'll go to the persistent memory. And finally, if there is a crash, the persistence buffer will be lost. The things that haven't committed to persistent memory will be lost. But the persistent memory itself will be retained. And finally, at some non-deterministic points in time, the writes in the persistent buffer will be committed to memory as expected. Right. So you've heard me talk about persistency model. I've mentioned that name a couple of times. But what is actually a persistency model? So a lot of you will be probably familiar with consistency models. And consistency model talks about, it describes, formalizes the order in which the writes by different threads are made visible to other threads. Persistency model, on the other hand, talks about the order in which the writes are persisted to memory. So you're very much familiar with a consistency model such as sequential consistency, total store order in TSO, and so on. And for the persistency model, there are a couple of models out there. The most significant one is the epoch persistency model, which we will talk about very briefly. So when we started looking at this epoch persistency model, we realized that there is no formal account of epoch persistency in the context of some mainstream hardware, realistic hardware. And this is the problem we set out to solve. So we want to add epoch persistency on top of some realistic hardware and see what its semantics looks like. So we talked about, I mentioned epoch persistency and talked about that it describes the order in which writes are committed to persistent memory. So let's look at some of those orderings. So here I have a more sophisticated program. Initially, x and y are 0, and I write 1 to x and y. Now, there is a power failure, and after I've run the recovery routine, like we said, because these persists are asynchronous, it's possible to see that none of them have persisted, or both have persisted, or the first one has persisted and the second one hasn't. But more surprisingly, it's also possible to see that the first one has not persisted while the second one has. In other words, persistence does not respect the execution order, and it may be in any order. and this is, again, for performance reasons. And most of the time, this is fine. But occasionally, you might actually want to constrain this and say, you know what, there is some kind of invariant I need to preserve, and I want to make sure these are ordered properly. So the epoch persistency's answer to this problem is this primitive instruction called the persistent fence, pfence. So essentially, if I put a persistent fence in between these two instructions, the persistent fence says all the writes prior to the fence will have to persist to memory before all the writes after it. So in this case, this pfence makes sure that the write to x is persisted before the write to y, so I'll never see this outcome of 0, 1. More generally, under epoch persistency, these are some of the ordering constraints. So the writes to the same location will always persist in the execution order. So in this program here, I have a write to x in A and another write to x in C, so A will persist before C. But the writes on different locations, like the example we saw on the previous slide, are completely unconstrained, unordered. So for instance, in this example, x and this A and B, the writes to x and y may persist in any order. And we've already seen we can constrain that with this pfence instruction. And what the pfence does is it divides the execution into these different epochs, hence the name epoch persistency, different phases of execution. So here, by putting a pfence here, I introduce two epochs, the first epoch and the second epoch. And the writes are always persisted in this epoch order. So here, all three writes in the first epoch, A, B, and C, are persisted before the write in the second epoch, D. Right. So we've talked about pfence. So what are the other things that could go wrong and you might want to eliminate? So we've seen that we've eliminated that 0, 1 behavior, but we can see that at the end, it's still possible to see this 0, 0 outcome, as if nothing, you'd done nothing, so all of your work is lost. And again, this is for performance reasons, because persists are asynchronous. They're sitting in the buffer, and most of the time, this is OK. But occasionally, you might want to say, you know what? Hold the execution. Do not continue past this point until all the work I've done so far is persisted to memory. And the epoch persistency's answer to that is this primitive instruction called psync. And a psync is strictly stronger than a pfence in a sense that it has exactly the same ordering constraints. But additionally, it's synchronous, which means that when I hit a psync instruction, I halt execution until all the pending writes in the buffer are flushed to memory, to persistent memory. And only then I will continue. So here, for instance, the psync halts execution until all the writes in C1 have been flushed to memory. So if I replace that psync with a pfence with a psync here, by the time the execution of this psync is completed, I'll know that the write before it, i.e. this write to x, is definitely persisted to memory. So if I later on if there is later on a power failure or a crash, I'll know that the write to x has persisted, so I'll definitely see x is equal to 1 in either case. Right. So back to our simple hardware layout. So the picture is a little bit more expanded now. So again, the writes write to the persistent buffer. The reads first read from the buffer. If there is anything, otherwise they'll go to memory. And if there is a crash, the buffer is lost, the memory is retained. But more importantly, the persistent buffer itself is divided into these epochs of execution. And the writes are always committed to memory in this epoch order. So here, all the writes in this first epoch are pushed to memory before all the writes in the second epoch, and so on. And of course, we've seen that to introduce new epochs, we use this pfence instruction. So every time you issue a pfence, you essentially add another epoch at the end of the buffer. And to flush to make sure that all the writes, our pending writes, are committed to memory, we use this psync instruction that says flush the entire buffer. So far, we've only talked about sequential programs. But as many of you know, concurrency is the root of many evils, or in our case, the root of many interesting problems. So what does it mean? Like we said, we wanted to add epoch persistency on top of some mainstream hardware that supports concurrency. So we looked out there, and of course, these are the available, but the x86 TSO, the PowerPC, the ARM v8, and we decided to focus on TSO because it was the simplest out there that was still not sequentially consistent in that it allowed weak behaviors. So before I go ahead and talk about how we've actually done this, what does it mean to add epoch persistency to TSO? Let me briefly tell you what we've actually done in the paper. So if you want, you can go have a look at it. So this is a list of our contributions. Like we said, our first contribution is this model called PTSO, which is the integration of epoch persistency with the TSO memory model. And we have defined its semantics in an operational way, so we have an operational semantics. But we also have an equivalent declarative semantics, for those of you who know, and we've seen in the previous talks, it means execution graphs, events with edges in between them, and acyclicity conditions. And we have a proof that actually says that these two semantics are indeed equivalent. Our second contribution that I'm going to talk about later on is that we actually wanted to show that PTSO is a reasonable model, in a sense that we can write programs under this model and we can reason about these programs and show that they are correct. But I'll come back to this briefly. Right, so we want to add epoch persistency on top of the x86 TSO, but what is TSO? Like we said, it's a weak memory model in that it's not like sequential consistency, they allow some weak behaviors. One of the most well-known weak behaviors is called this store buffering behavior, which I think we saw it in the first talk. And it's basically a program with two threads. In the first thread, you have a write to x and you read from y, and in the second thread, you symmetrically write to y and read from x. So let's look at a particular execution of this store buffering example. So the first thread executes. So I should have said that in the TSO memory model, the hardware layout is basically as displayed. I'll go back one click. So I have multiple threads because I'm in the concurrency setting. And obviously, each thread is going to be communicating with the memory, read and writing from memory. But additionally, each thread has this local buffer. So it means that every time the thread issues a write, he will add it to the buffer. And every time these writes in the buffer will be non-deterministically pushed to memory. And every time the thread tries to read from something, it will first check its local buffer, and then if there's something there, it will return it, otherwise go to memory. So back to our store buffering example. So let's see what happens. So the first thread writes to x, like we said, this write will be added to the buffer. And now the second thread does similarly writes to y, so he will add this write to his buffer. At this point, the first thread takes over and tries to read the value of y. And like we said, he will first check its own local buffer to see if there is an entry for y. In this case, there isn't, so he will go to the main memory. But the write by the second thread to y hasn't yet been pushed to main memory, which means that this thread will return the old value 0 for y, and will read 0 for y. And symmetrically, the second thread will try to read from x. He will check his buffer. There is no entry for x, so he will go to the main memory. And again, the write by the first thread hasn't reached the memory yet, so he will read the old value 0. So it's possible for both of the threads to read 0 and 0 for x and y, which is a behavior not allowed by sequential consistency, hence the weak behavior. Right. So we want to take this TSO, and at some point in the future, these two threads decide to push the writes to the memory, so eventually we will have 1, 1 in the memory. So now we want to take this TSO model and add epoch persistency on top of it. So from our simplified sequential hardware, we went to TSO by adding multiple threads, with each thread having its own local buffer. So we want to now take our sequential epoch persistency hardware and add it on top of TSO. So what should this look like? It's actually very simple. So again, we will have multiple threads. And each thread will have its own local buffer. And additionally, we have this persistence buffer shared in between all of them with the main memory. And again, the sequence of the actions of reads and writes are very similar. So every time a thread issues a write, the write will be added to its local buffer. The local buffers, the local caches, are eventually evicted to persistence buffer. And the writes in the persistent buffer are eventually persisted to memory in the epoch order. Every time a thread reads, it checks its local buffer first. If no entry there, will go to the persistence buffer. And if no entry there, will eventually go to main memory. The remaining instructions, like pfence and psync, are exactly as we described. Every time you issue a pfence, you will add a new epoch in the persistence buffer. And every time you issue a psync, you basically force the persistence buffer to be evicted to persistent memory. Bless you. So this was the first part of our contributions, the PTSO model, and I've given you an informal account of what this operational semantics looks like, and like I said, we have an equivalent declarative model. So the first part for this next part of the talk, I want to actually convince you that PTSO is a reasonable model, and that we can write programs under this model and verify them. So writing programs that actually with the correct recovery mechanism isn't straightforward. So what we've done in the paper, we've come up with this programming pattern that says, so long as you write through programs in this style and your recovery mechanism in this style, it's relatively straightforward to recover, to write them correctly. But what does it actually mean for the programs to be correct? This is the next part, which talks about persistent linearisability and adaptation of the notion of linearisability that existed out there. And finally, we have verified several examples under this notion of correctness. So, so here is the code in our paper, which is an adaptation of the Michael-Scott queue implementation, and it's intentionally zoomed out. But I wanted to show you that it's not easy to write it in a sense that all the code in black, which isn't much, is the original implementation. And everything else in blue is to do with persistence and correct recovery. In particular, this right-hand side is entirely to do with recovery. So it's not that straightforward. So we have said that if you have this pattern, you can show it correct. But what does it mean for an implementation to actually be correct? So for those of you in the know, traditionally, a correctness condition known in the literature for concurrent implementations is linearisability. So linearisability says, OK, let's say you have a queue implementation. To show that this queue implementation is correct, you would have to show that for all client programs of this queue implementation and for all executions of this client program, certain conditions hold. So here I have an execution of the queue library where the first thread tries to enqueue1 and then enqueue2, and the second thread is calling dequeue, and it's actually dequeuing value 1. So we want to see if this execution is linearizable or not. So the first thing we have to do is to define this happens before relation. Intuitively, happens before says which call in real time, which of these calls happened before the other one. So one standard way of defining this happens before is to say that E1 happens before E2 if it ends in real time before the second one begins. So for instance, in this example, A ends before B begins, so it happens before B, whereas A and C overlap in the sense that A ends after C has already started, so they're not happens before related. So once we've defined this, for this execution to be linearizable, we will have to find a sequential execution, otherwise, or else find a total order on all of these events that respect the happen before order, and additionally form a legal sequence. So what does it mean for it to be a legal sequence? That's library specific. For instance, in the case of the queue, for it to be a legal sequence, it will have to respect the FIFO, the first in, first out property. So here I have 3 events, and my only happens before constraint is that A happens before B. So these are my 3 candidates for total order. So in the first one, if I enqueue1 and then enqueue2, A, B, and then call dequeue, it's perfectly all right under FIFO to return the first value C. So this one respects the FIFO property. Whereas this one, if I start by calling dequeue, because the queue is empty, I shouldn't be able to return 1. So that does not respect the FIFO property. But linearizability requires there to be at least 1 candidate that satisfies this property. And here we have 2 of them, so this is a linearizable implementation. To give you an example of something that's not linearizable, for instance, if I replace that dequeue1 with dequeue2, again, happens before, everything as before, and these are my 3 candidates. But none of them are linearizable now. Because, for instance, if I enqueue1 and then enqueue2 and then call dequeue, I can't return to it because that violates the FIFO property. I will have to return 1. So what does this all mean in this persistent setup where programs can additionally crash and some events may not actually survive the crash? So I have intentionally faded this out because we will define the happens before relation in exactly the same way as before. But instead of saying find the total order on all the events of the execution, because some of the events may not survive the crash, we say find the total order on a subset of events, S. And again, this total order on a subset of events will have to respect the happens before. It will have to be a legal sequence. And additionally, this subset, you can't cherry pick it completely. You can't say, I want to see this and that. It will have to have certain properties. And one of those properties, for instance, is that it has to be prefix closed with respect to HV. What does that mean? For instance, if you choose to see B, you will have to see everything else that happened before it. You can't ignore those. Another property, there are a couple of others, basically says that, for instance, if you have a sync instruction, p-sync instruction that you choose to see, you will have to see everything before it, because p-sync forces you to have persisted all those events as well. Right. So here I choose my subset to be the events A and C. I ignore B because it didn't survive the crash. And this is perfectly all right. This is persistently linearizable because if I enqueue1 and call dequeue, I can return 1. So what about multiple crashes? Because we want our model to be general enough that survives multiple crashes. So essentially, I start executing the program until the first crash, at which point I call the recovery mechanism. And at the end, I will resume the execution of the program and run it until the next crash and so on, until the program execution is completed. So essentially, in this last phase of the last era of execution, I will have no crashes. the program is completed to execution. So what does it mean for this multiple crash execution for this chain to be persistently linearizable? So let's give us some names to this, like this is era 1, era 2 to era n. For this chain to be persistently linearizable, exactly as before, you will have to first, individually for each of these eras, you will have to show that they are persistently linearizable. And additionally, you will have to show that the concatenation of all those total orders that you found, like the total sequences that you found for each of these executions, if you put them together, it still yields a legal sequence. And that's our general definition of persistently linearizable with multiple crashes. So with that, I'd like to conclude, and I hope that I've convinced you that PTSO is a reasonable model. We have defined it formally, operationally, and declaratively, and we have, like I said, we have this programming pattern that kind of somewhat streamlines the programming, and we have this correctness condition, persistent linearizability, and in the paper we also have multiple examples of, for instance, we have Michael Scott queue implementation, a locking queue, a counter implementation. So I do encourage you to go and have a look at that. And that's all I have to say, and thank you very much for listening.
So we have some time for questions. Yes.
Thank you. On your definition of persistently linearizable, I have a question.
Okay.
In the area of transactional memory, there's a concept of opacity.
Sorry.
In the field of transactional memory, there's a concept of opacity, which is a correctness condition. How is your concept of persistently linearizable related to that?
So the honest answer to that is that I don't have the formal definition of opacity in my mind, and this notion of persistent linearizability was not completely our invention. It already existed in the literature. We have adapted it for our model. But I do suspect that they are very closely related because, after all, the opacity was to make sure that transactions that are bought were behaving reasonably. So.
Nice work, by the way. I like the programming model aspects of this, especially. I was hoping you could comment a little bit about programming model aspects when we're not operating at the edge of the memory model. For example, we have this notion of data race-free programming that is the model that most people operate in most of the time for programming languages with weak memory models. Is there a similar notion here?
So, okay, so this is something we're currently working on. So that will be a part of our future work. In particular, we're actually looking at what does persistence mean at the language level. So far we have integrated it with the hardware, with the TSO. The next thing we're doing is we're talking to ARM, another candidate for architecture, but we're also looking at language level persistency at the C11 level. And with that, we're looking at finding reasonable idioms that will, so if so-and-so conditions were satisfied, you have this notion of persistent data race freedom that your programs will behave properly, and you won't have to learn. But that's future work.
Okay, let's thank the speaker again.
Thank you.